like to welcome you to today's webinar titled Subsurface Analytics Digital Transformation of Reservoir Management with AI and Machine Learning, presented by the distinguished expert, Dr. D.Mohaghegh. Dr. D.Mohaghegh is a pioneer of artificial intelligence and machine learning. I think I'm facing some problems, sorry. So Dr. D.Mohaghegh, a pioneer in the application of artificial intelligence and machine learning in the exploration and production industry. He is a professor of petroleum and natural gas engineering at West Virginia University and the president and CEO of Intelligent Solution Incorporation. He is the director of West Virginia Leeds Laboratory for Engineering Application of Data Science, including more than 30 years of research and development in petroleum engineering application of artificial intelligence and machine learning. He has authored 3 books: Shale Analytics, Data-Driven Reservoir Modeling, Application of Data-Driven Analytics for the Geological Storage of CO2. More than 200 technical papers and carried out more than 60 projects for independent NOCs and AOCs. He is SP Distinguished Lecturer 2007 and 2020, and has been featured 4 times as the distinguished authors in SPE Journal of Petroleum Technology. He is the founder of SPE's technical section dedicated to AI and machine learning. Dr. D.Mohaghegh has been honored by the U.S. Secretary of Energy for his AI-based technical contribution in the aftermath of the Deepwater Horizon incident in the Gulf of Mexico, and was a member of U.S. Secretary of Energy's Technical Advisory Committee of Unconventional Resources in 2 administrations. Finally, Dr. D.Mohaghegh represented the United States in the International Standards Organization on Carbon Capture and Storage Technical Committee. Now, please join me to welcome Dr. D.Mohaghegh. It's a pleasure to have you among us today. As a reminder, if you have any technical questions, please feel free to drop it in the chat box down below. Now, without any further ado, Dr. D.Mohaghegh, the mic is yours.
Thank you very much. It's very nice to have this conversation with all of you. The topic is subsurface analytics, which is digital transformation of reservoir management using artificial intelligence and machine learning. I asked, and I was told that it should be about 1 hour. So I'm going to try to take my presentation for about 45 minutes, maybe 50 minutes, and then I will be available for question or conversation that you guys, ladies and gentlemen, that may have. So with that, let me get started. I'm going to start with some explanation first. What subsurface analytics is, it's an important part of what we call petroleum data analytics. What petroleum data analytics is, it's the engineering application of artificial intelligence in petroleum industry. And what artificial intelligence is, it's a new generation of science and technology. It's going to change a lot of things in the past few decades. It's a new generation of professional, engineers, like almost all of you guys who are here in this presentation. In 21st century, everything is going to be about AI on a regular basis. So it is incredibly important that you all get interested in artificial intelligence, and you have the expertise of petroleum engineering. But it's very, very important to spend a serious amount of time in order to have a good understanding of what AI is. the topic that I will be talking about today, I'm not going to go over the details of what AI is. I'm going to have some of that, not a lot of detail. But if you guys are interested, maybe that would be a different presentation at a different time. Today, I'm going to talk about the artificial intelligence, the way it is used in reservoir management, reservoir modeling, reservoir engineering, and so forth. I'll try to talk about AI a little bit because as I will talk to you about, unfortunately, it's the state of AI in our industry is not very good. And it has to do, I will try to explain very shortly in this presentation a little bit, and I'll be happy to answer any question that you might have. So let me go ahead. As I said, subsurface analytics is one of the major parts of petroleum data analytics. What is petroleum data analytics? What it is that it is application of AI and machine learning in petroleum engineering, and it uses data. However, it's very important to learn how it uses the data because in the past, statisticians and statistics uses data as well. And a lot of people think this is the same thing, but the answer is no, it is not. It's very different. So PDA, petroleum data analytics, is use of data as the starting point, as the foundation, as the main building block for analysis, workflow, modeling, and decision-making. What it is not, which is very important to learn and to know about it, what petroleum data analytics is not, it is not the application of traditional statistics in petroleum engineering. Traditional statistics have been used in petroleum engineering for more than 70 years, folks. So AI or PDA is not the same thing. We have not been, it's not what we've been using it for decades, okay? And furthermore, it is not an IT-related discipline. What IT is, information technology, is the use of computers to store or retrieve data and information. That is not what petroleum engineering, petroleum data analytics is. It uses it, it is important, but it's not the same thing. Furthermore, which is very, very important, I need to mention that and answer any question that you might have. There's a lot of articles that I have written on this topic. What PDA is not, it is not the combination of mathematical equation with AI and machine learning. That's one of the major problems that we currently have in our industry, even for those people who say they're using AI. Anyway, so with that simple explanation, let me continue. PDA completely changes the role of data in modeling physics. Data is not there to serve our current understanding of physics, because that's how it is today, prior to the AI and machine learning, even after using traditional statistics. The data traditionally in our industry is there to serve our understanding of physics. We have understanding of physics, we make a model, and then that model tells us what kind of data we should go and bring in order to be able to build the model or use the model. PDA is not like that. PDA completely changes the role of data. The entire physics is modeled using data, not using mathematical equations. That is the major difference between petroleum data analytics and traditional way that we have been using physics. However, it is incredibly important to learn that domain expertise, if you're solving petroleum-related issues, you have to be an expert in petroleum engineering, reservoir drilling, completion, production, so forth. If you're a mechanical engineer, or if you want to solve the mechanical engineering and you want to use AI, then you have to be an expert in mechanical engineering, in chemical engineering, depending on what kind of problem you're trying to solve. So in the context of petroleum data analytics, PDA is highly inspired by physics and geology. You will see when I start presenting to you the way subsurface analytics solves reservoir engineering problem, which is the topic of this presentation today. And you see how important it is for you to know the physics and geology of petroleum engineering. However, the physics and geology in the context of PDA, they are not deterministically or rigidly formulated. Again, no mathematical equation in order to identify how do they behave. Another idea is that's very, very important is PDA uses hard data to reach its conclusion, not soft data. What is the difference between hard data and soft data? I'm going to show you the hard data. Hard data is all the field measurements, all the facts, all the reality. Soft data is the type of data that is generated by engineers, which is based on assumptions, based on interpretations. PDA does not use that. PDA, which is use of artificial intelligence and machine learning, the key behind it is that it avoids assumptions, it avoids interpretation, it avoids simplification. PDA avoid preconceived notion and avoid any kind of bias. PDA is modeling using AI and machine learning based on facts, facts only, measurements, field measurements, reality, not what we think, not what we believe should be happening. That's the major difference. So what is the hard data? In the context of what we do in petroleum engineering, well placement, well trajectory, well log, core analysis, scout, seismic, PLT, ILT, well test, workovers, completion design, hydraulic fracturing implementation, injection detail, operational conditions, artificial lift, well productive. Everything that I'm talking here is things that in our industry we measure. None of the things that we come up with as an idea. And I will show you a few of them actually and see the difference. One more item, let me talk about for about 2-3 minutes, and then I'm going to go to reservoir engineering and explain what this technology is. And that is the state of the artificial intelligence in the petroleum industry today. In the past 7-8 years, the state of AI and machine learning in petroleum industry has been very poor, unfortunately. The AI and machine learning for the overwhelming majority of service companies and vendors is all about business. It's all about marketing, making money, and has very, very little to do with science and technology when you see what they are doing. And the question is, okay, how can operating companies, the management, how can they realize the realistic state of AI and machine learning if a service company or a vendor comes to them and say, hey, give us money and we're going to bring AI to your company? So how do you know what to do? Well, let me give you some examples. There are two major issues associated with the service companies and the vendors, and that is the problem that we had in our industry in the past decade at least. These are the two items. Item number one was that when we started it, not we, the operating companies, they used AI experts that had no petroleum engineering domain expertise to bring AI to petroleum engineering. And that caused a lot of problems. And the other one, after we talked a lot about that and told them how bad idea that is, I actually have it. And if you go to YouTube and type my name and say PetroTalk, there is a whole talk that I have about this AI experts that do not have petroleum engineering domain expertise. It's only 10 minutes talk that I had for SPE a few years ago. And another one is then, okay, if that case, I keep saying you have to have domain expertise, then domain expert. But the problem right now is there are a lot of domain experts that do not have a good understanding of AI. They have a superficial understanding of it. They think if I know the mathematics of the machine learning algorithm, the neural network of fuzzy systems with genetic algorithm, then that's it, I'm done. I'm an expert. Well, that's not the case. Knowing the mathematics of the machine learning algorithm, it's only 10% of what is required to become an expert in AI and machine learning, how it's used in petroleum data analytics. So let me go in a little more detail. Is that when the domain experts have superficial understanding of AI and machine learning, they call statistics, traditional statistics, they call that machine learning. And then they use what they call hybrid model. What is hybrid model? Hybrid model when they use mathematical equations to generate data and combine it with the data that is measured. And some of them call it physics-based mathematical equations and physics-based AI. A lot of names they gave it to it. When they talk like that, you know that they don't understand the technology well. And another one is the use of non-engineering application of AI and machine learning for engineering problem solving. In other words, what Google does, what Facebook does, what Netflix does, they're fantastic users or the fantastic developers of the AI and machine learning algorithms. Don't get me wrong. However, they're not solving engineering related problems. They're solving general intelligence, which is, to be very honest, in many cases is more complex than engineering application. But nevertheless, there are no requirement to have engineering domain expertise to do that. As long as you do have the general intelligence, then you need to be an AI expert, not a domain expert. And that's the difference. And for example, the general application of AI developed tools such as convolutional neural network and long short-term memory, LSTM. And the problem is when people try to use convolutional neural network and LSTM to solve petroleum engineering problem, because they think, okay, if it solved image recognition, if it solved object recognition, voice recognition, it should be able to solve reservoir engineering. That's not true. When you say that, when people say that, that tells you how little they know about this technology. There's a whole lecture that I have for this, but I'm going to stop here and continue going on subsurface analytics. So anyway, subsurface analytics is a non-traditional, completely physics-based simulation and modeling technology. It's all about physics, okay? Why? Because it's engineering application of AI. The question now, how physics is modeled in subsurface analytics? Well, it is modeled through field measurements, actual real data. It avoids major assumptions and simplifications. It avoids mathematical equations, and it is based on knowledge and domain expertise. Therefore, subsurface analytics is a combination of your knowledge and the data. We call it data knowledge fusion technology. And it is based on explainable AI. That's a whole new thing that I, in the other lecture that I mentioned, I'll talk about that, but I'm not going to talk about it today. But this is something that engineering application of AI dealt with it more than a decade ago. While only a few years ago, in 2016, US Department of Defense brought it up and said you have to build AI in a way that you have to explain it. And the The problem is when you do non-engineering related problem, then it becomes a very issue. And as US Department of Defense was absolutely correct, you have to be able to do it, and people are still having issues with it, and they still cannot do it. There are many research that is being done in Stanford, in MIT, in other universities for non-engineering application of explainable AI. But in petroleum data analytics, it's completely explainable AI. And again, that's another, I have articles in this that I can share with you if you're interested. So subsurface analytic, which is the application of AI and machine learning in upstream oil and gas, can be applied to conventional resources, and it can be applied to unconventional resources. In conventional resources, when it's applied to mature fields, we call it top-down modeling. When it's applied to green field or mature field in a different way, we call it smart proxy modeling. In unconventional resources, we call it shale analytics, when it does completion and production optimization of shale. And we call it dynamic shale analytics when it tries to predict and mitigate frac hit. Given the fact that this, I'm presenting this to you here in the middle, in Algeria, if I'm not mistaken. So my understanding is what's more important to you is the conventional resources rather than unconventional. Unconventional is very important in the US, in some other countries, but conventional resources is more important to Middle East, Africa, and Southeast Asia, and so forth. So I'm going to talk about top-down modeling here in the subsurface analytics. It's a purely fact-based field measurement driven reservoir simulation. I'm going to give you some examples of it. Top-down modeling, first and foremost, it's a couple simulation model. It couples reservoir and wellbore. It is purely based on field measurement. There is absolutely no equations that is used. It's fully automated and full field history matching. That's one of the major differences that it has with numerical reservoir simulation. I'm not sure how much experience you have on history matching, full field history matching of numerical reservoir simulation. We'll talk about it a little bit. I'll show you how TDM works. And it does blind validation in both time and space, and the result that it provides, it does sensitivity analysis, uncertainty quantification. Most important, it does field development planning. So what is the difference between top-down modeling and traditional numerical reservoir simulation? Let me give you an explanation of what that is. I'm going to show you the AI-based reservoir modeling versus traditional numerical reservoir simulation. So AI-based reservoir modeling takes an opposite approach when it is compared to traditional numerical reservoir simulation. Let's take a field. As you can see, you have wells, and you drill those wells in the completed in the reservoir, and in order to build the model. So if the reservoir here is in the bottom, and then you can see these well has been completed in the reservoir, that is the bottom of the this whole process. In the bottom, and so what do we do in traditional numerical reservoir simulation? First, we'll go to GNG people, to geophysicists, geologists, petrophysicists, and we ask them to model a geological formation. They do that, and then that geological model is used for the numerical reservoir simulation in order to history match the production that is right on the top, as you see, where the wells are. That's where the production, the oil and gas and water comes out. And the fact is it never works. Then reservoir engineers modify the geological formation in order to build a history match. So they go from bottom to top. So that's why the traditional reservoir simulation, numerical reservoir simulation, is a bottom-up modeling. It starts with the space, which is the bottom, and then brings in the time from the top through mathematical equation. So that's what we've been doing for 70 years, and I've been teaching numerical reservoir simulation for 25 years at the university. So that's what we do. However, what does AI and machine learning does? What top-down modeling does? Well, it starts with the top. It starts with the measured production, measured operational condition, using measured historical production from the top. And then it history matches the production using measured reservoir characteristics. It brings it out and try to find out this measured reservoir characteristics, what kind of geological model is developed. I'm going to explain that to you in a few minutes as part of what TDM is. That's why it's called top-down modeling. Top-down modeling is not a marketing name. It's a scientific name that explains how we go from how we use AI to build the reservoir simulation using AI and machine learning. Therefore, top-down modeling starts with the time, what's on the top, and then brings in the space, which is the through-field measurements. So that's the difference between these two technologies. One more thing that's very important to mention is that TDM couples reservoir and wellbore. And TDM does not require flowing bottom hole pressure. That's what we do in numerical reservoir simulation. We need flowing bottom hole pressure. Well, the fact is, in historical data, how many times flowing bottom hole pressure is measured? Hardly ever. That's why when you do numerical reservoir simulation history matching, you do not use oil production that's actually measured. You do not use that as an output. You use it as an input. Why? Because you want to measure flowing bottom hole pressure. That does not happen in top-down modeling in AI-based system. All inputs in top-down modeling can be optimized. Therefore, choke setting and wellhead pressure are used as input, not flowing bottom hole pressure. You do not use, why? Because hardly ever you have that kind of measurement. That's why we say reservoir and wellbore combined. TDM uses gas lift as input, so it can be optimized. It uses wellbore completion as an input, therefore that can be optimized. It optimizes as an output oil production, GOR, water cut, reservoir pressure, and water saturation. So what is the deliverables of TDM? Oil production optimization through OPEX and CAPEX. What is OPEX? Operational condition issues, so you don't have to drill new wells. Oil production enhancement through operational condition optimization, through injection optimization, through completion in the new reservoir formations, and through reopening certain abandoned wells. That's what in OPEX it does. And in CAPEX, it enhances through identification of where to drill new infill location for producers and for injectors. So enhancement of reservoir management through TDM, concerns associated with traditional, so what are the problem what are the concerns that is associated with traditional numerical reservoir simulation? We have been doing it for decades. What's the problem with that? Well, how do you handle it when you have missing data, right? And another problem is geological modeling. I'll tell you, because as I said, the geological model is developed by G&G people, right? They give it to reservoir engineers, and you never ever get a history match with the geological model, that the original, the basic one that was given to you. So what do? You have to change, modify it in order to get a history match. So that's another issue. Another one is operational conditions. We don't ever use it. Another thing is history matching. So the question is, how long does it take? I'm not talking about the university. When you go work for a company in the real world, how long does it take you to get to complete a history match? Well, the answer is It's a function of how much time do you have. If it takes 2 weeks, then that's how much it takes you to do the history match. If it's 2 months or 2 years, you keep doing it, because there is no way of coming to a complete history match at a given time. It is not a automated process. It's there are process with statistics that help you do that as you use different reservoir simulation models. But again, it is not a fully automated process. Another thing is production allocation. I'll talk to you about that as well. So the production that comes into the surface, where does it come from? If you have a multiple layer that you have completed in, much of it come from top or the bottom or the, what is it? Where does it come from? We do PLT, right? Production measurement, right? Anyway, so, and then do we ever do blind validation in time and space with numerical reservoir simulation? Really, we don't. So top-down modeling handles all of these concerns, and it uses AI to take care of that. And again, it does it without any assumption. It does it without any interpretation. It does it without any simplification. And that's what I'm going to explain to you now. So let's talk about the third part. How do you handle missing data? Using AI and machine learning rather than assumptions and mathematical equations to come up with or to handle the missing data, right? So let me show you how we do it in TDM. So one of the major characteristics of mature field is the fact that always some static or dynamic data is missing in historical data. And there are 3 categories. There are wells with no missing data. You have all the data, static and dynamic, that you have. Hardly ever happens, but there are, if you have 100 wells, you probably have a few that are like that. However, there are wells that are partially missing data, a certain percent of static data, a certain percent of dynamic data. Overwhelming majority of the wells in a historical field have this problem. And of course, there are wells that completely missing data. And of course, that's not overwhelming majority, but you definitely have some of it, them as well. So let's find out how to deal with it. First, or as an example, we're going to use wellhead pressure. Let's assume that no missing, if you don't have no missing data for a well, remember the first category, that no missing wellhead data. So here what you're looking at on the top, on the y-axis, you have the liquid measurement on the left and gas measurement on the right, and x-axis you have the date. So literally, this is production as a function of time for a particular well, and on the bottom you have wellhead pressure versus date. The x-axis is the same in the bottom and in the top. So if you look at it for that, what does that mean? That means for every specific time step that you have gas production and oil production or liquid production, then you have a wellhead pressure. And literally in this data that you look, for every single production that we do have wellhead pressure. By the way, what you're looking at, everything I'm showing you is actual data. It's not academic data. It's actual data from fields in Middle East or Egypt or Southeast Asia, where we have done TDM for. So if all the data is available, it looks like this, right? How about if it's partially missing data? This is another well. And if you look at it here, for example, the wellhead pressure is missing. You do have the production, but you don't have wellhead pressure. There are places that you do have wellhead pressure for the production. There are places that you don't. Here, another part that you see, you have only one for so many different. And here, this is what's called partially missing wellhead pressure data. And this one is completely wellhead pressure is missing. You don't have any wellhead pressure, but you do have production, right? So how do we handle that? First, what we do, we say well's history missing. So what you're looking at, you have 3 categories. You have, this is for one particular well, and you have the dates, right? And wherever you see green color, that means oil production is available, wellhead pressure is available as well. When you have red, that's the date when you do have oil production, but you do not have missing. You do not have wellhead pressure, it's missing. And finally, where it is red, I'm sorry, where it's black, that means both are missing. There is no wellhead pressure, there's no production, therefore you don't need any wellhead pressure. This is for one well. This is for an amount for here, you can see the amount of missing wellhead pressure is about 20% in this particular well. It's from a field in Southeast Asia. Every line that you see is a particular well, and it tells you how much data is missing. Some 100%, some 15%, and you can see the date. So how do you handle that? This is, let's say this is well location, one of them, that this is the one location that we call it blind validation of IDP. IDP is intelligent data patching, using AI to generate that data from the other data that's already available. Your entire well, so we have all the data, wellhead pressure, let's say, for this well, but we left it out and we used every other data to generate that to find out whether it's correct or not. And let me show you. So what you're looking at, these dots, again, this well was not used to build the model, AI-based model. It was used to find out the model you built was correct or not. We left it out, but now we're testing it. And so the red dots that you see is actual wellhead pressure, but the blue ones, as you see, that is what we generated using IDP, and you can see how correct it is. This is another one. Again, these wellhead pressure data that we had. We didn't use it to build the model, but after we built the model, we were trying to figure out from the production to see if it is possible for us to be able to generate wellhead pressure. Here is the results, as you can see, IDP, wellhead pressure, intelligent data patching. So this is how we handle that. Another thing is geoanalytics. What is geoanalytics? Geoanalytics is different from, it's AI-based geological modeling rather than traditional geological modeling. In traditional numerical reservoir simulation, what do? First, you ask the geologist to build a geological model, and they develop it. We call it original and basic geological model, and they give it to the reservoir engineers. The basic geological model never, ever results a history match, okay? And it has to be modified. So the basic geological model must be significantly modified to achieve a reasonable history match. This is what we do in numerical reservoir simulation. So history matching of numerical reservoir simulation is a long procedure. How does it work? This is what numerical reservoir simulation is. The original geological model is developed by geologists and give it to reservoir engineers. Reservoir engineers try to history match it. It doesn't get a match. So what do? We modify the transmissibility around every single well. If you use any numerical reservoir simulator, CMG, Eclipse, or any other, they provide you with an opportunity to change the transmissibility around the well. What is transmissibility? Transmissibility is a function of porosity, permeability, thickness, everything that literally should be measured. We modify it until we get it, when we don't get a match. And we keep, what does that do? It modifies the geological model that we're getting. Do we do it once? No, we do it continuously. Sorry, this doesn't work here, until we succeed. And when we succeed, the final geological model is very different from original geological model that we received, and then we use that in order to production optimization. However, in traditional geological modeling, development of the basic original geological model is based on field measurements. They use well log, cores, seismic, but they perform assumptions, they do interpolation, but the most interpretation, the most important issue in traditional geological model is spatial interpolation. So, which the reservoir characteristics between the wells, and they use kriging and radial basis function to do that. Let me explain to you very quickly I'm sure you all know that, spatial interpolation. So in a spatial interpolation, if you have 3 wells in this reservoir, right, and you have a porosity in every location, then what you do, you say, okay, if the porosity there is 4 and here is 10, then between them is something in the middle. So literally what you do between 4 and 10, that in the middle should be 7. Between 10 and 16, in the middle should be 13. Between 16 and 4, in the middle should be 10. That is spatial interpolation of the reservoir characteristics, and that was traditional geological model is developed. So if this is actually what you're looking at, it's an actual offshore field in Southeast Asia, and if they do that, existing production wells, and these are existing injection wells, so these are the distance between the wells, and this is how you identify what is the reservoir characteristics between them. And this is how, if you're doing the gamma ray, right, this is how you identify what the gamma ray distribution is, because you identify between these 2 measurements what is in the middle. You're using space only. In geoanalytics, you don't do that. You use space and time. So how do you do that? Instead of geological, in general, in traditional modeling, you build a geological model of the reservoir formation, you give it to the reservoir engineers, and reservoir model is built by modeling fluid flow in porous media, and you modify the geological model, and that's the traditional. In TDM, in AI-based, is the other way around. We use the data from the field and we build the geological model. So AI-based geological model is developed based on AI-based model, and it is not the traditional is a spatial interpolation. The AI-based model is spatial temporal interpolation. You interpolate it not only based on space, but on the space and time. This is due to the fact that fluid flow in porous media, one of the things we learned, the fusibility equation, it's both about space and time, not only space. And when you do that, look at the porosity in the traditional modeling. This is a field, again, in Southeast Asia. This is porosity. When it is traditionally done only a spatial interpolation, you see the values of the porosity at every well. If you do that in spatial temporal interpolation, you see the difference in distribution. So let me show you more of that. We start with static data, but also we start with the dynamic data in geoanalytics. First, we use the dynamic data to do fuzzy pattern recognition, and then we use that and furthermore dynamic data to develop dynamic conductivity mapping. Then what we do, we use the fuzzy pattern recognition, dynamic conductivity mapping, the dynamic data and the static data, and we develop spatial temporal interpolation that I told you that allows you to generate the geoanalytics. Then all of this data goes to the geoanalytics. And what we first do, remember, as I said, dynamic conductivity map. How do you develop dynamic conductivity map? I'm going to give you an example. This is the same field. These are the production wells. These are injection wells. The first thing you have to do is to identify that injection wells is impacting these producers. This injection is impacting these producers, and as we move forward, when we put all of them, this is the communication of injectors with the producers. And those communication and interaction becomes very, very important. We have to take care of that. However, every producer is impacted by other producers. So here, this well is impacted by these offsets, this by these offsets, this well by these offsets, and I keep going with every single well, how offsets are going to impact it. When I put them all together, what do I get? I get that interactions. And then we have producers offset and injection offsets. So we bring them all together. Now I have all these interaction between producers and injectors among each other. That comes from the time, not only from space. When I use that and the actual space measurements I generate, I identify that communication between them, which one is higher, which one is lower, and that provides me an opportunity to identify the conductivity of dynamic mapping. This becomes the dynamic mapping. This is dynamic conductivity map. This shows you the communication between the wells. It's about time. You bring that to the So I'm going to use that in gamma ray. The gamma ray that I showed you, if I only use a space, this is what gives me. If I do a space and time and dynamic conductivity map, this is for exactly the same geological model, but the difference of distribution you can see. When you go to density, this is the difference. When you go to clay volume, this is the difference. When you go to resistivity, this is the difference. When you go to formation top, this is the difference. When you go to formation thickness, this becomes the difference. When you go to porosity, this becomes the difference. When you go to permeability, this becomes the difference. When you go to initial water saturation, this becomes the difference. So you see, AI-based geological modeling becomes very different. And another thing to do, you can use this dynamic conductivity map in order to find out how production throughout time changes the location also of the oil that remains in the formation. So here what you're looking at, this is dynamic mapping of remaining reserve as a function of time. As you saw in the beginning, it shows you the original oil. I'm going to do it again in a minute, but the first thing that shows you what the distribution of oil is, and then for every month of production, it tells you where it's coming from, where it remains, and now you have the distribution here, and this is your recovery factor. The same is we do it for pressure. Now, this is original pressure. This is injection and production as a function of time creates this change in pressure. So in order to find out where to drill, you get both injection and pressure distribution. So I'm going to go one more time to show you. Remember, this is the original oil in place distribution that we learned through geoanalytics. Now, as I showed you before, I'm going to show you one more time so you can see it. It shows you where you drill and produce, and when you drill and you inject, how it's going to change this distribution as a function of time. You can see the wells that are coming in and being abandoned. How is it going to change? And this tells you after so long production, where is the remaining oil, and this is how you identify. This is the remaining pressure as a function of thing. Now the question is, when you do this, this provides you with an opportunity to find out where to drill or where to complete. Let me show you example. Infill well location. This is in the Middle East offshore field that we did. Actually, we did this, and this was presented by one of the managers of this company 2 years after we did this. We didn't know that, and then we asked them, are we allowed to present it? They said yes. So they're looking at these 4 wells. These 4 wells, 3 of them were identified where to drill using a traditional numerical reservoir simulation. One was what we did for them in TDM. We told them where to drill, right? And let's see what happened between them. So first and foremost, we're going to show you comparing the infill well location recommended by TDM versus what was recommended by numerical reservoir simulation. And what we're showing you is the average production rate during the first 6 months of production for every single well. And we did this in April 2020. And look at that. This well, which was by numerical reservoir simulation, it was drilled in 2013. And until this time, there was 86 months. And its average 6 months, first 6 months of its production, only first 6 months, the average was 1,522 barrels per day it was producing. This one was in November 2014. It was drilled for 65 months. However, in the first 6 months, the average was 1,300. This one was drilled in 2015. These 3 were numerical reservoir simulation for after 62 months. But the first 6 months, the average was 1,300 again. This is the TDM we told them to drill in 2018. Only 22 months until this April 2020 that we did. The first 6 months of it was 2,156 barrels. I'm going to repeat that instead of 6 months, because this was 22 months, we take 22 months of each wells and then find out the average. So this is during the first 22 months for all of the wells. This one was 1,600, this was 1,300, this was 1,400, and what we provided was about 2,000. That's the difference. So it's 1150 actually. I can go to other things, but I'm going to stop it because we almost gone to an hour, and I'm going to answer any question. And if you want, probably some other time, I can show you the rest of the things. I don't want to go beyond, since you all want to be here for 1 hour. So I'm going to go ahead and stop the presentation and answer any question that you might have.
Okay, sir. So thank you so much for this insightful and instructive webinar. So we'll be jumping to some of the questions. Okay, so to see the questions. Okay, so our first question is, which of the known AI applications are used in PDA? And if this, can you tell us if artificial neural networks are used in?
Okay, so in PDA, in Petroleum Data Analytics, what we use, again, this is what we have been using since 1991 in research and development. We use three algorithms, three applications. One is artificial neural network, one is fuzzy set theory, and the third one is evolutionary computing, which part of it is genetic algorithm. So these are the three that we use mainly.
Okay, sir. Thanks. So for the second question is, can we really rely on physics and data interference approach to understand our reservoir and replace the classical simulation which requires high computation time and a huge amounts of data? Or can we think about it as consulting work which can be done for legacy fields that miss a lot of data?
Can we really rely on a physics and data interference approach? Actually, that's what we have been doing for the past 70 years. We have been using a mathematical, because you rely on physics. If you mean relying on physics, AI completely relies on physics, a lot more than we have been relying on physics prior to AI. The only difference is how physics is modeled. Prior to AI, we were modeling physics through mathematical equations, and it has to do with our understanding of physics. So when you do, our understanding of physics allowed us to generate a diffusivity equation, right? And diffusivity equation tells us to go measure porosity, to go measure permeability, to go measure thickness, and bring them in, and then measure viscosity, measure you know what, right? So in mathematical equation, our understanding of physics tell us what to do or which data you get, right? However, are you using directly gamma ray and resistivity in diffusivity equation? No, you're not. You're using them in order to calculate porosity and then use the porosity in there. Now, is your calculations correct? In porosity, to a very large extent, the answer is yes, it is very, very correct. But is that true everywhere? Not really, right? One of the major question I have for you, for example, production allocation. How do you do production allocation? How do we do production allocation in the past 70 years? How do we do that? Through KH, right? Permeability and thickness. So the question is, fluid flow in porous media is all about space, not about time? That's not true. It's about space and time. Diffusivity equation have both space and time in both. So why do we use only space? KH is only space. There is no time, right? So that's what the detail, the key is. And also I showed you about geological modeling, the geoanalytics, will bring in time outside of what we used only as space. That's what the real reality of the physics is much better model using AI than we have used it in the past. So it says, can we really rely on physics? Yes, we are relying on physics through data to approach, understand our reservoir. And that's again, so we have been understanding of our reservoir and doing what we were doing in the past 70 years. So the question is, can we do better now that we have a better technology? The answer is absolutely yes. That's what AI does. The only thing is you don't combine them. Because combining them is literally no help. It's using exactly the same thing you've done before, we just call AI because it's sexy. People think if I say AI, I'm going to do exactly the same thing in a little different fashion, but I'm asking for a lot more money for doing
that. Thanks, sir. So our third question is, how accurate are these numbers? Basically, he's speaking about, I think he stated an example. He said, for example, the porosity and permeability prediction in PDA are time and location estimated, but how close these numbers are to field measurement?
Oh, they're absolutely, they 100% close to the field measurement. They use actual field measurement at every well. Exactly the same thing that traditional ones does. So there is no change on the value of the porosity and permeability where the well has been drilled and that was measured. That is not going to change whatsoever. The difference is the porosity and permeability between the two field measurement, right? Because traditionally we use only a space to find out what's between them. In geoanalytics, you use space and time to find out what's between them. Why? What is time? Pressure and saturation. Does pressure and saturation change production? Of course. And that production tells you what's happening at every location. You know it at the well, but the question is, does the production is only a function of porosity and permeability of where the well is? Because where the well is, the porosity and permeability that we measured, where does it come from? It's either come from core, it come from well log, right? Well log's only 6 inches away from the well. Core is actually in the well, right? So we have measurements at the well location, but we don't have it away from it. But the production comes from away, not only from that location. That's why you need to do time and space rather than only time. I hope that answers your question.
Yeah, I think it's clear enough. So another question is there any open source data that we can perform top-down modeling on it? And if can, please you can share.
Okay, so let me show you one thing. I'm going to share with you 1 second. There is not an open source, but what there is a book that has been written. Let me share my screen for a second with you again. This is the book that I wrote in 2017, and it was published by SPE, Society of Petroleum Engineers. Actually, they asked me to write this book, and it's called Data-Driven Reservoir Modeling. And unlike these service companies or other vendors that they tell you they use AI, but they don't tell you what they do, top-down modeling literally, it shows you step by step in every detail how you can build it. So we share that as an academician, so we don't do anything that we say you cannot have. So we have shared this. So all the details of how to build a data-driven reservoir model or top-down modeling, you can use this to do it. But no, we do have at the ISI, we do have a software, but we do not provide that as an open source. But you know, the same thing is true about numerical reservoir simulation, right? You know how to build it. There's only one book, but in numerical reservoir simulation, there are tens of books that show you how to do it. And when you take the course at the MS or PhD, at least this is what I have done when I got my graduate degree, and I did it to all my students. So when I teach them, we teach them how to build it. They build it, they're not going to use that, but at least they have to build it to make sure they follow exactly how it goes. I hope that answers the question.
Thanks. So I think it remains 3 questions basically. So For those who, I think he's speaking from a geomodeling perspective, he said, for those of us that are geomodelers who do not have AI fundamentals, what is the way forward?
Okay, sorry, I didn't get it. Which one was it? Okay, we do see results, right? Or which question?
I can repeat it, sir. He said basically that I think he's a geomodeler or he's basically studying geomodeling. He said that basically he doesn't have AI fundamentals, so he's asking how he can do. He said, what is the way forward to learn more AI in order to implement it with the geomodeling?
Yeah, the only way that comes to me, again, you have to deal with the model by there are multiple things, folks. So let me ask you this: when you take a numerical reservoir simulation course, right, and you build a numerical reservoir simulator, I have a question for you. Can you do it in your freshman year? No. You have to get your bachelor's degree in petroleum engineering. When you go to master or PhD, then you do that, correct? So my question to you, the same thing is about top-down modeling. Is it possible for you to do that without knowing anything about AI? Well, I'm not saying you shouldn't do that. Go ahead and do that. Go through the book and find out. But the main thing is you need to learn what the AI and machine learning is and what it does. One of the things I'm going to do right now, I'm going to, through this chat, I'm going to send you my email address. This is my email address. I just, through the chat, I provided to you. Send me an email. I'll provide you with an AI primer for PDA. It's a document that includes a lot of, it only includes links. It links to videos, links to articles, links to books, anything that's available. And it literally starts with neuroscience and then artificial intelligence in general, neural network, fuzzy set theory, and then about PDA. So if you are interested, send me an email. I'll send you that document and the link. So my point is that it is not fair to think that if you just look at the mathematics or look at the essence of top-down modeling, you can build it from scratch. Well, it's going to take some time. I'm not saying you shouldn't do it. Please, please, please go ahead and do it. But don't think that immediately you're going to get the results, right? That's how Eclipse was generated. T-Navigator was generated. CMG was generated. It took decades, right? So the same is true about this one as well. Those only required domain expertise and the computer science, right? This one requires computer science and domain expertise, but also understanding of AI and machine learning. So in other words, if you do not think that by going through these process in a couple of months, and that's what the problem right now we have in vendors and some of the startups and some of the service companies, they think it takes them a week to figure out how AI works if they learn the mathematics behind it. That really doesn't work. It's all about philosophy. It's all about neuroscience. It's all about biology. It's all about computer science. All of these are required above and beyond your domain expertise. So my objective is to excite you enough to go in that direction and learn them. But don't think you can learn them in 1 week or 1 month, and that's it. When people who come up with this idea, that means they don't understand AI. That's a very interesting technology. It takes time. Give yourself time, and hopefully, can you become an expert? Yes, you can. But it takes time and it takes efforts. Exactly the same way it took you to become a reservoir engineer.
Thank you, sir, for clarifying this. So I think we have another question. What are the inputs of dynamic conductivity maps? It is just time, or there are another features changing to time?
Good question, and that's why I couldn't go into so much detail. I didn't finish it. What you will need. So yes, do you need time? Yes, you need time step, right? However, what you need is every single measurement of fluid that is generated, combining oil, gas, and water, because that's come to the surface before it's separated, but that doesn't matter at the separation. So not only that, also what matters is operational conditions, the wellhead pressure, choke setting, if any gas lift injection took place, artificial lift that took place, flow line pressure, all of that provides you that communication between two, not communication, but importance of, if you have three wells, well number one with well number two versus number one with well number three. The communication between these two wells, which are offset of each other during the time that both of them are producing. That tells you, as a function of time, pressure and saturation between these two, how it's being modified. That helps you to identify the difference between the two measurements that you have in the middle.
So our last question is, he's saying at the beginning of field development, there is not too much data about production. Would it be a problem to use the top-bottom method at the beginning?
That's a very, very good question. You're absolutely correct. That's why top-down modeling is for mature field, not for green field. For green field, we have another AI-based technology. We call it smart proxy. I'm actually writing a book right now about it. And there's another book that I have written on that topic that's called Data-Driven Analytics for the Geological Storage of CO2. That shows smart proxy to a certain extent because that is green field. But yes, top-down modeling, what I talked about, is all about mature fields where there's already wells, there's already data. You're absolutely correct.
Okay, sir. So basically, there is no more question related to the topic, but I think one question, even me, I want to ask you, sir. So basically, you said that, or you emphasize a lot about, how to use AI with basically domain expertise. And I think actually I'm working on machine learning project in my dissertation project. And when I go to the exploratory data analysis and try to analyze basically the data based on my project or basically the theory, I find always difficulties to relate basically, the domain expertise, since I don't have too much.
I didn't get it. You always have problem by, I didn't get that sentence. Could you repeat?
I will repeat
that sentence?
Yes, I said basically when I'm going through the exploratory data analysis, so I am struggling with kind of relate basically theories, what I understand about the theory project, my project basically, and to relate it to, how to analyze data and how to find basically the impactful features basically in my data set. So from a prediction perspective, because I'm working on prediction model.
Okay, so that's something I lecture on. Another thing that I mentioned to you at the beginning that has to do with definition of machine learning. So the thing is why domain expertise is so important in the problem you're trying to solve using AI, machine learning, the engineering application. The reason is because it's called machine learning, right? So in order for machine to learn, you that are doing this, you need to teach. Teaching creates learning. Without teaching, the learning has a completely different way. It's not very, very correct. It's not very, very good, right? So the key is you have to use the domain expertise in order, but keep one thing in mind. You cannot teach through mathematical equation, you cannot teach through physics, you cannot teach through using English or Arabic or Farsi or Spanish language, right? The only thing you can do is teach through data, because the machine doesn't speak a language, doesn't know mathematics, doesn't know physics. The algorithm can only learn from the data. So you have to use your domain expertise, not to generate data, but to put the data in a fashion, or literally, that's called another thing called feature engineering, to come up with a way to use the data to teach the machine learning algorithm what it has to be able to do, especially when you use a supervised version of it, right? So everything comes down to one question. What is the problem you're trying to solve? That tells you what to do. Nothing other than that. That's very, very important. Okay, so it is another problem that in engineering, I don't think is very correct, is to give you a general idea what to do. Yeah, I can give you a general idea what to do in my lectures about AI and machine learning. However, that general idea will never help you to solve a very specific problem. You have to keep doing it, using understanding the general ideas, then come up with your domain expertise, bring them together, and try to teach the machine learning algorithm what you're trying to teach it. And then based on that results that you get, come back and forth, back and forth, back and forth until you get better and better and better. This is a process. Again, it is very different from how you use diffusivity equation and mathematical equation to solve problem. That's one of the problems. That's why I think what I mentioned, the state of this technology in oil and gas industry is not very, very good right now, because it's pretty unfortunate how people in the service companies and some of the startups come up with what they have to do. It's really very little about the science. It's a lot about marketing. So again, to answer your question, unless I cannot understand what exactly the problem you're trying to solve is, it's very hard to answer it. Those books explain a lot of things about TDM. There's another book I wrote about shale analytics. If you want unconventional resources, and smart proxy is going to be another one that's being published very soon. So in other words, the problem you're trying to solve, as long as you have the domain expertise in that problem, then your experience in AI is not going to happen immediately and make you solve it, but it's going to take you in a direction that eventually, hopefully, you'll be able to solve it. I hope that answers your question.
Yes, thank you, sir. So actually, I'm working on some production problems, but I prefer basically, say, send you an email about the details. So later on. So I think with this, we are done here. So thank you so much, sir, for accepting our invitation for this insightful webinar. I hope the attendees get so much insight about AI, and especially today's webinar about subsurface analytics. And I think just to remind you that this session has been recorded, and you can find it in our YouTube channel.
Thank you.
Thank you so much, sir.
Have a great day, folks.
Have a nice day.